All right, let's get right into it. Today we're talking about something really cool, a totally different way to think about training AI. Forget just throwing more compute at the problem. We're going to explore a new frontier that's all about geometry. Yeah, you heard that right. We're going to see how forcing an AI model to live on a curved surface can solve some of its biggest problems, making it way more stable and efficient. So, the conversation in AI is always about scale, right? More data, bigger models. But this paper asks a really interesting question. What if the secret to building better AI isn't just about getting bigger, but about having a better shape? What if the key is actually better geometry? Okay, so to really get why this geometric approach is such a big deal, we've got to start with the problem. And it turns out the very foundation of today's biggest AI models is, well, it's pretty unstable. Think about what's going on deep inside one of these giant models. You've got all these tensors, the weights and gradients, and as the model trains, these numbers can just go wild. They can balloon up to infinity or shrink down to zero. It's like trying to build a skyscraper, but your steel beams in concrete are randomly expanding and contracting. The whole thing is just fragile.
And that fragility leads to a ton of headaches. You get numerical overflows and underflows, which are just fancy words for your math breaking. Your optimizer starts taking these crazy, unpredictable steps, and oh man, tuning hyperparameters becomes an absolute nightmare. The bottom line is, for these massive, complex systems to work, you need some level of certainty. You need the internal parts to be predictable, and right now, they're not.
So, how do you fix this? How do you force that predictability? Well, this is where the genius of the idea comes in. We're going to completely change the rules of the game. Instead of letting our model's weights just wander around in this flat, infinite space, we're going to constrain them. We're going to force them to live on a very specific curved surface. Now, the proper math term for this kind of surface is a manifold. And don't let the word scare you, the concept is actually super intuitive. Just think about the Earth. We all know it's a giant sphere, right? It's curved. But when you're just standing in your backyard, it looks perfectly flat as far as you can see. That's a manifold. It's a surface that's curved on a large scale, but looks flat when you zoom way in. And that locally flat part is key. It has a name, the tangent space. You can literally picture it as a flat plane that's just touching the curved surface at one single point. For our optimizer, this is huge. It's basically the set of all the legal moves it can make at any given point, all the directions it can step in without immediately falling off the curved world it lives in. Okay, so see how this geometry creates a much smarter optimizer? A standard optimizer, like Adam, kind of just takes a step and hopes for the best. If it goes too far off course, it tries to crudely yank itself back. But a manifold optimizer is way more elegant. It does its calculations in that nice, flat tangent space to find the perfect direction. It takes a precise step, and then it does a retraction, which is a very specific, calculated move to land perfectly back on the curved surface. And the best part? The learning rate, which is usually just a loose suggestion, now becomes almost exactly equal to the actual distance you move. That gives us an incredible amount of control we just didn't have before. All right, I know this can sound a little abstract, so let's make it super concrete. We're going to look at the simplest possible case, trying to optimize a single vector that's not allowed to leave the surface of a sphere. It all boils down to this really simple three-step dance. Step 1. You figure out the best possible direction to move, but you do it in that flat, easy-to-work-with tangent space. Step 2. You take a step of a very specific length, that's our learning rate, in that direction. And finally, step 3. You retract. You pull that new point back onto the curved surface. That's it. Find the direction, take the step, and pull it back. Simple. So if we look at the math behind it, and don't worry, we'll just look at the meaning, the goal is pretty straightforward. We want to find an update step that gets us as close to the solution as possible. But we have two really important rules. Rule 1, the step has to be a specific length, which is our learning rate. No more, no less. Rule 2, the step has to be in the tangent space. It has to be a legal move. By turning it into this constrained optimization problem, we can find the absolute perfect step every single time. Okay, so that was for a single vector on a sphere. Pretty cool, but neural networks aren't made of single vectors. They're made of massive matrices. So now let's take this core idea and scale it up to the big leagues, the weight matrices inside a real neural network. To do that, we need a different kind of manifold, one that's designed for matrices. It's called the Stiefel manifold. And what is it? It's basically the set of all perfectly well-behaved matrices. These are matrices that are guaranteed not to shrink or explode vectors that pass through them. How? Because all of their singular values, you can think of those as their stretch factors, are forced to be exactly 1. By making our weight matrices live on this surface, we are building stability directly into the geometry of the model from the get-go. Now, besides the surface, we also need a way to measure distance. And the choice here is really clever. They're choosing a distance function to limit the maximum stretching effect of the update. What they're using is called the spectral norm, which basically measures the most a matrix can stretch any vector. By using that as our ruler, we gain yet another layer of precise control over the training process. And what's so cool is you can see how different choices here create a whole family of optimizers. You know, your standard vanilla gradient descent, that's just optimizing on a flat Euclidean space with the regular Euclidean distance. But when you combine our special Stiefel manifold with that powerful spectral norm, well, that's when you get the star of the show, the manifold Muon optimizer. So the million-dollar question, does all this fancy geometry actually work in practice? Well, the results speak for themselves. In this experiment on CFAR 10, manifold Muon didn't just beat Atom W, the go-to workhorse optimizer for almost everything these days. It beat it by a pretty significant margin. We're talking a 4% absolute jump in accuracy. That's not just a small bump. That's a really, really promising signal. And here's the proof of why it worked. When they actually looked at the weight matrices after training, what did they see? The singular values were all clustered perfectly around 1. It's beautiful. This is the smoking gun. It shows the optimizer successfully forced the weights to stay on that Stiefel manifold. The model got all the stability benefits we talked about, and that directly translated into better performance. The theory held up perfectly. Okay, this is awesome for a single layer, but a real network has tons of layers all stacked together. So how do you guarantee stability across the entire network, from input to output? This brings us to the next big idea, modular manifolds. The thinking here is brilliant. You start treating every piece of your network, a linear layer, an attention block, whatever, as its own self-contained geometric object. Each of these modules has 3 things that define it: what it does, its forward function, the special curved surface its weights live on, its submanifold, and the ruler it uses to measure distance, its norm. And here is where it all comes together. Once you define your network in terms of these geometric modules, you can create rules for how they compose. And when you stack them, the whole system can automatically figure out how to budget the learning rate across every single layer to keep the entire network stable from end to end. It's a truly principled way to build complex models that are stable by design, not by accident. So as we wrap up, it's really important to see that this isn't just about one new optimizer. This geometric point of view is a whole new paradigm. It's a new way of thinking that opens up a massive design space for how we build and train AI. And that leads to some really fascinating questions for the future. I mean, think about it. Right now, we build an architecture, and then we just slap an optimizer like Atom on it. What if we could co-design the architecture and its optimizer from the ground up, making sure they were a perfect geometric match for each other? And we could take it even further. Why should the whole network live on the same kind of surface? An attention head and an embedding layer do totally different jobs. So what if each component lived on its own unique mathematical manifold with a geometry that was perfectly tailored to its specific function? A kind of custom geometry for every part of the network. And maybe the biggest question of all ties back to hardware. We all want to train on cheaper, more efficient, lower precision hardware, but it's notoriously unstable. So, could this be the key? Could these geometric constraints, which enforce stability by their very nature, be the thing that finally unlocks stable training for massive models on way more efficient hardware? It's a powerful idea to leave you with. The path to bigger, better, and more efficient AI might not be paved with more silicon, but with smarter geometry.